5, 4, 3, 2, 1. Terms of entrapment. The structure and function of copper-zinc superoxide dismutase. Protein molecules govern biological functions in all living systems. X-ray crystallographic studies reveal the arrangement of atoms forming the three-dimensional protein structure and allow us to examine the relationship between structure and biological function. In this movie, we use computer graphics to illustrate the three-dimensional structure and function of the enzyme superoxide dismutase, which protects all aerobic organisms against toxic byproducts of oxygen metabolism. Superoxide dismutase is a dimeric molecule having two identical subunits of 151 amino acids, or 2,200 atoms. The two subunits are related by a twofold symmetry axis shown as a vertical red line on the screen. Each subunit contains two metal ions, a copper and a zinc, which are shown as spheres, along with the alpha carbon trace of one subunit. 11 sequences are now known from different species. Here we compare the sequences from the bovine and human enzymes, where the red regions represent the most variable changes in sequence, and the green regions represent conserved areas. Superoxide dismutase forms a Greek key beta barrel, which contains 8 extended beta strands, shown in green, connected by red loop regions. The two red loops shown in the front represent the active site of the enzyme. Here we look at a two-dimensional schematic and a three-dimensional view on top of the three-dimensional arrangement of the atoms in one subunit. If we focus in on the strands making up the beta barrel, or beta sandwich, there are 4 which we show independent surfaces for, which are fairly regular extended beta strands with good hydrogen bonding. The other 4 strands are less regular and more twisted, have more irregular hydrogen bonding, and form the beta barrel facing into the active site of a molecule. If we depict all 8 beta strands simultaneously and show thin cross-sections perpendicular to the axis of the barrel, we can look at the arrangement of the strands as they pack to form this compact structure. In 2 places, strands from opposite sides of the barrel connect across, strengthening and forming cross braces. Most of the other interactions take place between adjacent beta barrel strands. In addition to the structure of the subunit, we can examine the relationship of the 2 subunits to each other, which also contribute to the extreme stability of this enzyme. The enzyme has a melting temperature of 83 degrees and remains active under conditions where most other enzymes are denatured. The surface buried from solvent accessibility between the 2 halves of the dimer is about 1/10 of the molecular surface and covers about the same region as the area buried between the 2 halves of the beta barrel. Looking at the 2 surfaces buried from solvent contact, one belonging to each subunit, shown in pink and blue, we can see the interdigitation of the side chains and the complementarity of the surfaces. Color coding such that oxygens are represented with reds colors and nitrogens with blue, we can look at the hydrogen bonding and the hydrophobic characters seen here between 2 hydrophobic colored green valine side chains. Using computer graphics, we can separate the 2 halves of the dimer and look at the arrangement of the atoms on the buried interface. Here we use red dots to show the oxygens and blue dots to show the nitrogens scattered throughout the more hydrophobic surface contributed by the carbon atoms shown in green. On the right-hand side, an edge-on view of the interface shows an X depicting the twist of the interface. Changing the color scheme to represent the electrostatic potential contributed by the charges in the enzyme, we can see the red negative regions and the blue positive regions are located at the edges of the interface, and the center of the interface is roughly neutral, colored by green. The two active sites on the enzyme are located at opposite sides and centered on the copper ion, shown by a blue sphere. If we look at the electrostatic patterns on the surface of one individual subunit, we can see over most of the surface a rather random pattern. When we come to the active site, however, there's a large blue region representing about 1/10 of the surface of the enzyme, which codes the positive charges located around the active site. The vector field set up by the enzyme attracts the negatively charged superoxide substrate to the positively charged active channel. The active channel is about 12 angstroms deep, as shown in this cross-section. The superoxide fits into a pocket located immediately above the copper. The arrows point in the direction that a negatively charged substrate would follow on a path into the copper in the active site. The enzyme mechanism takes part in 2 steps. Here we're looking at the copper ion shown in blue and the zinc ion shown in purple. The superoxide transfers an electron to the copper in the first step of the reaction, and the bridge between the copper and the zinc, formed by a histidine ring, is broken. In the second step of the reaction, a second superoxide molecule picks up the electron from the copper and 2 protons, one from the histidine and one from solvent, to form hydrogen peroxide. Thus, in the 2 steps of the reaction, we take 2 superoxide negatively charged radicals and form 1 molecular oxygen and 1 hydrogen peroxide. Most of the residues involved in setting up the electrostatic field and in the mechanism are conserved among different species. Looking at the electrostatic fields around both active sites, we see that they form a wide solid angle around the enzyme, contributing to the efficiency of the enzyme and helping to explain why the dimer may be a useful feature. So we hope that this movie has helped to show you that having a detailed structure at atomic resolution of a protein molecule gives us an opportunity to understand the relationship of structure and function.